Hello, class. This is part 1 of our next section, section 1.8 on continuity. So the continuity of a function. This is where when the limit of a function x, the limit of a function as x approaches a can be found by calculating the value of the function at the value of a. The function then would be continuous at that point a. So when out function f is continuous at a if the limit as x approaches a of f of x is equal to that particular value f of a. Otherwise, if f is defined in an open interval containing a, except perhaps at the value of a, then our function f is discontinuous at a if f is not continuous at a. So something, for example, such as a jump or a break in the graph would cause that. A jump or a break. So, specifically from this definition, if f is continuous at a, f of a is defined, which means the value of a is in the domain of f. The limit as x approaches a if f of x exists. And then finally, the limit as x approaches a of f of x is equal specifically to f of a. Physical phenomenon are usually continuous, that being something such as velocity, height, so on and so forth. But discontinuities can occur in applications such as with electric circuits. So as an example, with example 1 here, we want to say at which numbers is f discontinuous, right? And we see a couple of immediate areas where we have that, right? We have a break right here at 3. We have the function not existing at all at the value of 1. And at 5, we have this dot here above the function and an open circle here at 5. So because of these 3 parts, the values that this could be at are values of x such as 1, 3, and 5. Just to make note why they're discontinuous here, for the value of 1, as I may note, there's an open circle there. So it's discontinuous at 1 because f of 1 does not exist. Despite the fact that we could technically calculate the limit, the specific value itself doesn't exist, so not continuous. At 3, we have that break. So because of that, even though, it is defined at 3, at f of 3, if we go from either the left or the right, the two limits, they do not exist. So because of this, it's not continuous at 3. So for at 3, that limit as x approaches 3 of our function, it does not exist. Because the left and right limits are not the same. And I just spelled the word exists wrong. Does not exist. 1 second. Okay, it does not exist. And then finally at 5, you could see, even though the limit definitely approaches a number, right? It gets this particular value of where this open circle here is. But f of 5, though, is a different number because we have it defined at this point above here. So at 5, it's discontinuous because the limit as x approaches 5 of f of x does not equal f of 5. Because of that, not continuous. Again, even though the limit, we do have a limit there, it is not the same. So because of that, not continuous. Moving along from that, with just these regular functions here, where are each of the following functions discontinuous? Right? So based upon this first one, x squared minus x minus 2, divide by x minus 2. For this, due to this denominator of x minus 2, this is only discontinuous. It's only discontinuous at a value of x being 2, which is when that denominator is equal to 0. And that's the only part where that's discontinuous. We'll be seeing it in a little bit, actually, but the reasoning for that, numerator is a polynomial, denominator is a polynomial. Both of them are polynomials. So the only time it won't exist, since polynomials are always continuous, is if the denominator is 0. So that's when x is 2 in this case. For b, f of x is equal to x squared minus x minus 2 divided by x minus 2. If x is not 2, we just saw it's discontinuous at 2 from part A. But now, for values of x being 2, we get a function value of 1. So, for us to look at that, right, in order for this to be continuous, we do need to look at that limit. This would be as x approaches 2 of a function f of x. And since it's approaching 2 and not exactly 2, we look at the function that we had from part A. So limit as x approaches 2 of, this is x squared minus x minus 2 divided by x minus 2. Nice thing about that is we can factor that numerator from algebra. So the limit as x approaches 2 of, factoring this lovely polynomial in the numerator, we get x minus 2 times x plus 1 divided by x minus 2. And we could see from that, as I change colors here, these x minus 2's, we could cancel them out. So this would just give us, and let me write that down here, the limit as x approaches 2 of x plus 1 now. Just that. And now look at that. That's a nice polynomial, right? Again, continuous everywhere. If we put the value of 2 into there, we get ourselves the value of 3. But we have a problem. We get a value of 3 here, but in our function definition, we are just given the value of 1. So, because the limit does not equal the value of the function, this is also discontinuous at x is equal to 2. For part C, f of x is equal to 1 over x squared if x is not 0, or 1 if x is 0. So, based upon this, if you looked at the limit as x approaches 0 of 1 over x squared, this might be helpful to look at as a graph. So let me pull this up for the sake of our discussion. So if we look at this, this is our function here, 1 over x squared. As we approach 0 from either the left, you could see our function values, they increase and increase and increase. If I zoom out, not zoom in, if I zoom out from this, you could see that they increase forever. They never approach a certain number. Likewise, if we took it from the right, you can see that these also increase forever and ever and ever. It does not approach a number. So because of it, this limit for 1 over x squared as x approaches 0 from the left or the right does not exist. So because of that, if we look at this limit here does not exist. So we are discontinuous at x is equal to 0. And then finally, this last function, f of x is equal to, this refers to as the step function. And for us to see that, let me just give you a basic idea of what that makes. That looks something such as this. We have a coordinate axis. And what the step function does, it rounds. Where we start at the value of 0, we have 1, 2, and so on. We would have ourselves a closed dot and then the function with an open circle at the next particular value. So it looks something like this. Each integer. What that means is the left and right limits at any value of the integer does not make a value because the left and right limits are not going to be the same due to that being a step function. So this limit, as x approaches any integer of our step function, which is basically an x enclosed in double brackets, this does not exist. For any integer n. So because of this, this is discontinuous at all integers. At all integers in this particular case. So with that being said, these continuous functions, right? We kind of been saying it a little bit, but a continuous function, it can be graphed without ever lifting the pen from the paper. Since it would just be, a continuous function if we just had something like that. Despite whatever equation that is, that's continuous, right? I didn't have to lift my pen from from drawing out that particular function. We could have something such as a removable discontinuity. So that would have been what we had seen. What we had seen in example 2. This is when we can redefine the function to remove the point where the function is discontinuous. And that happens when we have a hole in the graph. So this, as an example, would have been example 2. Right? For part A, we had that function x squared minus x minus 2 divided by x minus 2. And we had seen that if we started taking the limit, factoring that numerator, we got ourselves the function x plus 1 back. And we still saw it was discontinuous. But due to that, if we had used the value of the function to be something like this. So f of x would be equal to the x squared minus x minus 2 divided by x minus 2 for values of x not 2. But if we give it a function value of 3 like we found in part B, when x is 2, this would be an example of a removable discontinuity. where we are able to define the function at that particular value. So it breaks that discontinuity there and allows us to then be able to give ourselves that limit to be exactly the value it needs to be. For example, so if a function f is continuous from the right at a, if the limit as x approaches a from the right of f of x is equal to f of a, and f is continuous from the left at a, if the limit as x approaches a from that left of f of x is equal to f of a. A function f is continuous on an interval if it is continuous at every number in that interval. So just to quickly give an example here, I'm going to show that the function f of x is equal to 1 minus the square root of 1 minus x squared is continuous on the closed interval -1 to +1. So if we are within that interval, this time we're going to look at the open interval, -1 to 1, for the value of a. Then the limit as x approaches a of f of x, so this would be 1 minus the square root of 1 minus x squared. This is equal to, since we have those limit rules that we have seen in our previous section, this is 1 minus the limit as x approaches a of the square root of 1 minus x squared. This, again, from those limit rules, we could write as 1 minus the square root of the limit as x approaches a of 1 minus x squared. So now we are calculating the limit of a continuous function. It's a polynomial, 1 minus x squared. So we could just write that as 1 minus the square root of 1 minus a squared. And that simply is the value of f of a. So because of this, f is continuous. At a, if a is between -1 and +1. Mind you, that's for that open interval. We could see that the limit as x approaches -1, this being from the right-hand side of our function f of x. This, if we put in that -1 into here, we get 1 minus the square root of 1 minus -1 squared. This makes a 0 in the radicand. So 1 minus the square root of 0, this just gives us 1. And that is the value of f of -1. And the limit as x approaches +1 from the left-hand side, this of our function f of x, again, if we put 1 in here, we get that same value of 1, which is also the value of f of 1. So, due to this, we could see that f is continuous from the right at -1 and continuous from the left at +1. So it's continuous either side there up to the endpoints. So because of that, f is continuous. Over that closed interval, -1 to +1. So that's it for part 1 of this video on section 1.8. Be on the lookout for part 2. Thank you.